So, welcome everyone to lecture number 16 in the lecture Statistical Theory for Deep Learning. We have today two, as I think, lovely proofs. The first lovely proof is the end of the proof of theorem 3.5. We started already. You have maybe seen the beginning was ugly, was a technical proof, but the rest of it pretty nice. And what it's about? Well, we want to bound L1 mu epsilon packing numbers of some functions at G, functions from Rd to R. And we can do this by using the VC dimension of the corresponding class of subgraphs of this function, and the subgraphs of this function that calligraphic G is the ZG plus, consisting of all, where for each function small g in calligraphic G, you have some z, which is the z of all xt in Rd times R, so that t is less equal to f of x. So that's just the area around the graph of the function f. Although there should be a t is less equal to g of x, sorry, there's a typo error on my slide, of course. And then and we are interested in uniform bounds between the expectation and sample average of these of such function classes. We have seen that for these we need bounds on the covering number. We have seen that the covering numbers are bounded by packing numbers, and here's the bound on the packing number, which is useful. It's theorem 3.5. You have a natural number L and N. You have some range, some value b greater 0, describing you the length of the range of the function. You have some calligraphic G, which is a set of functions from R with exponent L to the interval from 0 to b. You have an arbitrary probability measure on RL. You assume that the VC dimension of this set of graphs corresponding to T, so VC dimension of G plus is greater or equal than 2. Then the L1 of mu epsilon packing number of G is bounded by 3 times 2EB divided by epsilon times log 3EB divided by epsilon with exponent VC dimension of G plus. That's our result. And we all already have seen, that was the technical part, that in order to prove this, it's sufficient to prove relation star. And relation star is the inequality, the L1 mu epsilon packing number of G is less equal than 3 times the shadow coefficient of the set of subclass G plus corresponding to G, with number of points is lower Gauss bracket b times epsilon, b divided by epsilon times log of 2 times this packing number. And we have seen this by using the result of Wapnick and Chervonenkis from 1971, that we can somehow upper bound the shadow coefficient by a polynomial in the number of points we consider with degree VC dimension of the set of class, and then you get some lower bound of, or then you know that the packing number is less than some polynomial involving this b divided by epsilon and so on, times this packing number with exponent VC dimension. And from this one, we concluded in the technical step that we get the answer. This was basically also the only point where we need that the VC dimension is greater or equal to 2. You will see in the remainder of the proof we will not need it, and therefore you immediately also see the theorem also holds if VC dimension of G plus is not greater or equal to 2, but you replace the VC dimension on the right hand side just by the maximum of the VC dimension at 2. And you don't need this as a G. Okay, but now the promised lovely proof, the proof of star. How to do it. Well, first of all, I want to bound the packing number, so I choose a packing of the maximum size. That's G bar, consisting of functions G1 to Gn. E and L1 of new epsilon packing. Of G, of maximal size. And then this maximum size is just the packing number. M epsilon G. Then I use as a shortcut, the k is the number of points in my number of points which I put into my shadow coefficient. So k is equal, so it's the lower Gauss bracket b divided by epsilon times the log of the covering number, and the covering number is the n. And then you see what we have to show is that the shadow coefficient and I will derive a lower bound of the shadow coefficient, that the shadow coefficient of G plus and M is greater equal, and I bring the 3 on the right hand, on the left hand side, m divided by 3. You have a question, please?
Yes, with k, shouldn't there be a logarithm of 2m?
Shouldn't there be a logarithm of 2m? Correct. Thank you very much. But that's nothing which we can fix. And maybe the hint, somehow this was the wrong point to point out this error here. You have to wait until the maximal damage is occurring. And then, just in the moment before you think the professor sees it himself, yeah, you raise your hand and come up with a section. That's the way I did it. This was how many years ago? Let me think about something like 25 years ago. 25 or 35? No, it was something like 32 years ago, and it was a lot of fun. Okay, good. Another question? no. After you know this.
In the shadow coefficient, I think we need k and not m.
In the shadow coefficient, I think you need the same point, yeah? Same point, yeah? See, I can tell you this again. Yeah? Good. Okay. Now we have agreed on that. How to do this? Well, the lovely idea is what is the shadow coefficient? Yeah? You might remember you pick k points from our points are from our L times R. We have k points, and we look on the number of subsets of sets in this set of subclasses, subgraphs. So we look at the number of subsets of these k points, which can be picked out by G+. So we looked at how many sets do you have of the form your k points intersected with sets from G+. And then the obvious, and then you take the maximum. And then the obvious question is how to choose these points. And what we do is we choose these points randomly. That's the first nice idea. And then the question is what is the proper distribution? Well, for x I just use the distribution u. And for the t, I choose the uniform distribution on the range from 0 to b. And I choose all random variables independent. So I have random variables. And how do I denote them? I have to look up for the notation. Do I use st? Or what kind of random variable? No, qt. So I choose random variables q1, t1 up to qk, tk, and I choose them independent. The variables. Such that the q1 to qk have distribution u, and the t1 to tk have an uniform distribution on the interval from 0 to t. Are uniformly distributed. B. Then I set Ri is equal to Qi Ti. That's my i's point. And I set R1k, that's the sequence of the k points. Is there a sequence or a set? In fact, I will use it more than set sequence, but let's mark it as a sequence. And then we want to use the packing. Then I use G bar, and we see G bar, the packing has the properties that all the functions in the packing, they are in our original function space. So the G bar is the subspace of G. So the class of subspace of subclass of G is of course a superset of the class of subgraph of G bar. So we will use this one also. Lower bound the shadow coefficient by entering here G bar. And then I needed location for the graphs. For G from RL to R, I said the graph of G is just its graph, that's the set of all xt t in RL times R, where t is less equal than G of x. That's my notation. And then we have no unbound. What I want to derive a lower bound on is Sg plus k. Yeah, my notation is not uniformly, that should be this kind of G. Sorry. G plus k. Of course, if you replace the set of sets by a subset of it, the shadow coefficient cannot increase. So that's greater equal than S G bar plus K. Now by definition, that's the maximum over all x1 x1 t1 until xk tk in our set I times r, and then I look at the number of subsets which can be picked out by G plus bar from this set of points. X1 T1 until Xk Tk. Here. And of course, if I now just forget about the maximum, but plug in my random terms, my random points, then it will be a lower bound. For each values of this random point, so also the expectation of the whole thing is a lower bound. And that's the main idea. And now I compute this expectation. And how to do this? Well, you use the definition there. So that's the expectation. Now the question is, what kind of notation do we use? Well, when we use the standard notation, then it's just the cardinality of a set here. It's the, you have this graph. Maybe I make it with GF, because that's a little nicer than G. Intersected was now considered as a point set. And F is from my value. That's the definition here. And I would like to make out of this a sum over the function in G bar. So a sum over the G1 to Gm. And I can get this sum if I make again a lower bound. You have the same set of sets. But I use only those f's in. Oh, there's a mistake here, sorry. It's not a plus, of course. That's G bar. I use only those f's for which I get a different set than for all other f's. So I use F element G bar and GF intersected with G, no, I forget the GJ, with R1K is not equal to the same as G R1K for all G in G bar which are not equal to F. So I add one more condition. And this one more condition enables me now to say, then these sets which I have here are all distinct by definition. So I just have the number of sets. So basically I have the number, I can count the number of F and G bar which satisfies this condition. And that's what I will use to compute the expectation. That's the same as the expectation. Sum over all F and G bar so that and I will use this as an indicator. Indicator condition is GF R1K intersected with R1K is not the same as graph of G intersected with R1K for all G element. And again, my notation. This should be calligraphic G. It's this kind of G. We are here. Questions?
Yes, we assume that G bar is not non-infinity, or what
G
happens
bar is not infinity. What happens if G bar is infinity? If G bar is infinity, you have some kind of problem because in your theory in 3.5, the left-hand side will be infinity and the right-hand side less than infinity. Because your VC dimension will be some number less than infinity here. It cannot be infinity. Any more questions? And now you see what I do. I compute this expectation. Well, expectation of a sum is the sum of the expectation. Expectation of indicator function is probability. So this is the sum of probabilities. Probability that GF intersected with R1K is not equal to the same as G intersected with R1K for all G bar F. Then this probability of this event is 1 minus the probability of the complement of the event. Minus probability and the complement, I just say that the for all is gets into an exist. Will the exist G in G bar we are here. And then the probability exists something is the probability of a union is less than the sum of the probability, is less than the number of sets in this union times the, or number of events in this union times the maximum of the probability. And so I can upper bound this by m minus 1, but I upper bound m minus 1 by m times the single probability, maximum. And then I can lower bound this by it's similar to sum bar 1 minus m times the maximum over all G in G bar without F of the probability GF okay is equal G on K. And we're here. And now what you see, what I need is that this is greater equal than 1 divided by 3, then I have greater equal m times 1 divided by 3, and we have our lower bound. Questions? Up to that point, please.
It's not precisely about the proof, but if we have G bar has infinite size, so our packing number is infinite, is then the VC dimension not also infinity? Because we can find infinitely many points that are at a certain degree distinct from each other. So we can just pick the set, or the VC dimension is the largest set that we can shatter, and then we can just pick all these points that are distinct from another. So we can't just, because these functions G are packing.
But you know this, I don't see it because you have the packing works with this L1 new distance, and the VC dimension works with uses points. I don't see the connection at the moment. Well, in our case, it cannot happen. It follows from theory. The theorem which I proves shows that this cannot be true here. The theorem shows that if the VC dimension is less than infinity, then this packing number must be less than infinity.
Yes, but if that then in some case implies what I just said.
And this implies if I show that our theorem implies the VC dimension less than infinity, then packing number less than infinity, then this implies by contraposition, packing number infinity implies VC dimension infinity. That's correct.
Okay.
But for this I have to prove the theorem. Yeah? And for a theorem I don't need to prove that, I don't have to consider the case that the packing number is infinite, because in theorem 3.5, if this is infinite, then the theorem cannot hold. Oh, okay, now maybe I see your point.
If the VC dimension is also infinity, then it does hold.
No, I think I see your point now. If the packing number is infinite, then I have no, but what you actually show that we don't need the maximum size. What you actually show is if you have a packing of finite size, then this finite size satisfies this condition here. And then this finite size satisfies this one. And I think you are right. There is a point here that you need to consider this special case that the packing number is infinite. And I don't see it, but I think it follows from the proof. So maybe ignore it at the moment, and then maybe I can tell you something about it next time. So, I've never seen that we need to consider this case special. I always thought it was clear, but I don't see it at the moment. But maybe up to that point. We are here, and what I want to prove now is that this one is at most 2 divided by 3, then the whole thing here will be at least 1 divided by 3, and then the whole right hand side will be m divided by 3, and I'm finished here. So we need an upper bound on this one. Then we look at this guy. So I choose 2 functions and consider this probability. G and R. This F is not the same as G. Then this probability. Same as G. Okay. Well, that means the first point is at one point z intersected with GF. And our point was Q1, T1. Is the same as if I intersect this with GG. I have the same for the second point, and so on until the case point. That's it. Now you see that our random variables are independent, and therefore the probability that these event conditions hold jointly, it's just the product of the individual probability. Independence. That's the probability independence of T1 until QK, TK. That is probability is the same. Probability that GF intersected with so we are here. Now you see our random vectors are also identical distributed, because the QIs are identical distributed, the TIs are identical distributed, and they're independent of each other. So you have this first probability with exponent n, with exponent k, and the unit f is equals T1. And we have k of these guys. And now again I use that this probability of the event is 1 minus probability of its complement. Because I can easier compute the probability of the complement. And maybe make two things at one. I make the probability of the complement I write as the expectation of the conditional probability of the complement given Q1. So that's this condition, and I make a conditional distribute probability, and I make an expectation. And we have this exponent k. And now what does this mean? Now we look at this graphs. You have somewhere some f, you have some other place, and you have the gf here. It's gf. You also have another function, looks this one. It's g. You have somewhere, you have the Q1. Do you have a third column? No, I don't have a third column. At some point I have a Q1. And where must T1 be such that the graph of subgraph of F intersected with Q1 T1 is, sorry, I wanted to write not equal to here, because I had a complement, is not the same as the subgraph of G intersected with Q1 T1. Maybe someone else than the front row. So you have to choose now here. You have Q1, so you have to choose now here. Well, we have somewhere we have our B. Yeah? Our B is our upper limit, or function lower than B. Yeah? We have a uniform distribution. And uniform distribution we choose from T1 from 0 to B, so the point will be somewhere here. And which part of this uniform distribution must it be such that the two intersections are not the same, please? Between the lines, yeah? Between these, you see, it has to be between, in this area, yeah? Here you only need the T1, then it's fine. So if I want to translate this in a condition, then I see it's the expectation that the probability, and then I don't know whether f of Q1 is less equal than G of Q1 or larger than. Here we have the case that G of Q1 is less than, so we have this one. But it could be also the opposite way, that f of Q1 is less than T1 is less than G of Q1. And then I have to compute this conditional probability. You have to compute the expectation. You have to compute 1 minus, you take this exponent k. Okay, any idea what this probability, conditional probability is? If you remember how we have defined the distribution of T1, you could see. Okay? Suggestions? If you look, the T1 to Tk are uniformly distributed on 0b, independent of Q1 and Qk. So this conditional probability is what? Well, because this Q1 is independent of the T1, this conditional probability means just you fix the value of Q1 and compute the value of T1, and then you plug in the random value of Q1.
Because T1 is uniformly distributed,
Yes.
which is the size of the interval.
Which intervals? There are a lot of here.
Yeah, the small one in between where it's 5.
This one where it lies,
Yes, and then we have to rescale with B a bit.
and then you will scale by the length, yeah? So it's either f of Q1 minus g of Q1 divided by b, or g of Q1 minus f of Q1 divided by b, but both time you can just rewrite it as an absolute value between f of Q1 and g of difference, absolute value of the difference between f of Q1 and g of Q1 divided by g. So we get here T1 uniform 0b, and Q1 independent of T1. We got 1 minus the expectation of my conditional probability is just f of Q1 minus g of Q1 divided by b. And the whole thing is exponent k. And remember, what I need is I need a lower bound on this. We want to show that this is do I need an upper bound, or what do we need? We need to lower bound this whole thing, so we need an upper bound on this, yeah? I need an upper bound on this probability. Yes, I need an upper bound of this probability. Now you can, the b is just a constant, it's 1 over b times the expectation of absolute value of f of Q1 minus g of Q1. Can anyone tell me something about this absolute value? Expectation of absolute value of f of Q1 minus g of Q1? What's that? If you think about the distribution of Q to QS.
Maybe it's the integral over the difference of f and g, and integrated with respect to the distribution u.
It's integrated with respect to the distribution Q of the L1 distance. It's an L1 distance, so it's the L1 new norm of f minus g. So this is the same as 1 minus 1 divided by b times the L1 new norm of f minus g with exponent k. By definition of Q1. And now, what do you know? Well, f and g was from g bar, two different functions, and g bar was a packing. So they have a L1 new distance of at least epsilon. Yeah. Well, this one is at least epsilon. So 1 minus 1 divided by b, this one is less than 1 minus 1 divided by b times epsilon. Is epsilon k. And that should do. Because g and g bar is f not equal g. And now we have just to put the whole thing together. I have to clean here, but remember we want to show that the shutter coefficient is greater or equal than m divided by 3. This should be enough. So what can I do now? I start with the here, ends. My shutter coefficient of the set of all subgraphs. Okay. That's greater this one. And here I plug in upper bound on this maximum, which gives me a lower bound here. And this upper bound doesn't depend on f and g anymore, so the sum just is the number of terms, which is m. Times 1 minus m times, and then I plug in my upper bound, one minus epsilon divided by b is exponent k. That's it. And I introduced k somewhere, and well, k was what's in the shutter coefficient here on the slide, but with the packing number replaced by n. Okay, but before I upper bound, maybe it's easier to see it in this way. You know that 1 plus x is less equal than e to the power x. Standard inequality, you plug it in with x equal to minus epsilon divided by b. So you see it's m times e to the power minus k times epsilon divided by b. You plug in the definition of k. That's m times e to the power minus, and I have said that k is the same as this term on the slide, right hand side, bottom line. So lower Gauss bracket, e divided by epsilon times logarithm of 2m. And that's it. and then the whole thing multiplied by epsilon divided by v. Now you want to get rid of the Gauss bracket. I want to make an upper bound of this, so I got rid of it if I replace this one by a lower bound, and then I get an upper bound, so that's the lower bound is this number minus 1. So we have m times e to the power minus this number, e divided by epsilon times log 2m minus 1 times epsilon divided by v. That should it be. I should not have given you the hint, because now you are not telling me if I make a stupid mistake again. That was a bad idea. Okay, but that's how life is. But what I used here, I used that this Gauss bracket is greater or equal than this one. Therefore, e to the minus this one is less equal than e to the minus this one. That's correct. So now you see what's happening. You can multiply this one, this cancels. The e to the power minus log 2m gives 1 divided by 2m. And then we still have something left. That's e to the power minus is plus epsilon divided by v. Correct. And then you know that epsilon divided by v is less than 1 divided by 4. So that's less than 1/2 times e to the power 1/4. Now you need the 4th square root of e. Yeah. And the claim is it's less than 2 divided by 3, something like this. So you have to do it with a calculator. That should be less than. So the 4th square root of e should be less than 4 divided by 3. So 4 divided by 3 is exponent 4. 1.3 squared is 1.69. 1.69 squared is should be greater than 3, yeah? And e was less than 3, so it should be okay. Hence we have this one, and then the whole thing is greater or equal than 10 times 1 minus 2 divided by 3, which is n divided by 3. And we are done. Questions? Any questions? Then I will need 5 minutes to clean the blackboards. It's 10:45, so we go on at 10:50. I would like to go on with the lecture. Maybe one hint. I've uploaded yesterday a complete version of the lecture notes on Moodle, so you can print out also the 4th chapter. And I will not write the 5th chapter. Although I originally wanted to write a chapter about optimization, there's no lecture left where we can deal with it. But we will deal with the optimization in the seminar, and there will be also a seminar talk in this lecture which will deal with optimization, so we'll see something about optimization. If you look what we did now, we proved in theorem 3.5, and I told you we need bounds on the covering numbers. We already know the covering number is always less than the packing number. That was a rather trivial number. We now have a bound on the packing number involving the VC dimension, so we need a bound on the VC dimension. And here is one classical result about a bound on the VC dimension. Theorem 3.6. We need the VC dimension of the graphs. Instead of the graphs, we consider something slightly different in case that we have a finite dimensional vector space. So that G be an R-dimensional vector space of real valued function functions defined on RD. And then I said the set of all sets A, that's the set of all x in RD, or set in RD, that G of Z is greater than equal to 0, and G is in cryptographic G. And we can later think about what this has to do with the VC dimension of the subsets, of the subgraphs. And then I have the following bound on the VC dimension of A. The VC dimension is less equal than the vector space dimension. Pretty simple statement, yeah? Okay. Then we prove I want to show that the VC dimension is less than R, so I show that R plus 1 points cannot be shattered by sets in A. So I show that there is I pick up arbitrary R plus 1 points. Let's set 1 to set R plus 1 in RD. And we show that there's a subset of this R plus 1 points such that any set in calligraphic A intersected with Z1 to ZR plus 1 is not equal to this subset. I define this subset by using an additional mapping. Find L. I use a mapping from my vector space of real functions, G, to R with exponent R plus 1. Where L of G, well, that's just the values of G at the point Z1 to ZR plus 1 written in one vector. So that's G of Z1, C of G of ZR plus 1. Of course, this mapping L is a linear mapping. Consequently, the image of this linear vector space G is this mapping is a linear vector space. It's in subspace of R with exponent R plus 1, and its dimension, you know, it's less equal than the dimension of G. Because you can just use the basis of G and map this to all possible points, and then you get then all the linear combination of those points gives you the complete image. So then G is a linear vector space of dimension less equal dimension of G, which was R. Hence you have an R-dimensional vector space, a subspace of R with exponent R plus 1. So I can find some vector gamma in R plus 1, which is not a zero vector, which is orthogonal to all vectors in G. The axis gamma, and this has R plus 1 components. It's not zero. Such that gamma is orthogonal to G for all G and G. Which means that if I consider the scalar product, then the scalar product is zero. And if you consider the scalar product, you have gamma 1, G of Z1, plus gamma R plus 1, times G of Z R plus 1 is equal to 0 for all G in G. And now, because gamma is not the zero vector, at least one of its components must be not equal to 0. And then this component is either positive or negative. And because I can multiply the whole vector by -1, I can assume without loss of generality that I find some components which is less than 1. So without loss of generality, we have gamma I less than 0 for some in 1 to R plus 1. Okay, now how to prove that the set of points Z1 to ZR plus 1 is not shattered by A? Well, I show that the subsets of all those of the indices 1 to R plus 1, where the corresponding Z1 to ZR plus 1, where the corresponding Zj is greater or equal 0, cannot be picked out by G. So assume that for some G and G, this Z, which we consider Z in RD, is greater or equal to 0. picks out from Z1 to ZR plus 1 the subset out of J, J1 to R plus 1, gamma J greater than 0. And I want to show that this is not possible. Why? Well, consider two cases. If gamma j greater than equals 0, then g of zj is greater than equal than 0 by this condition. And if gamma j is less than 0, then c of zj must be less than 0. Then, so g of zj times gamma j is greater than equal 0 for all j equal 1 to plus 1. And I have form I where gamma I is less than 0. For this I, g of zi must be less than 0. So for this particular index, gamma of zi times g of zi times gamma of I is greater than 0. And by choice of A, choice of I, g of zi times gamma of I is greater than 0. And does anyone see the contradiction?
Well, if they are all positive and one of them is really not non-zero, then the sum of them must be greater than 0, which is not 0.
If we look at the sum, this implies gamma 1 g of z1 plus gamma r plus 1 g of z r plus 1 is greater than 0, which is a contradiction. Contradiction. And maybe I call this star. And that's it. Questions, please?
Why can't g of zi be 0?
Why can't g of zi be 0? Because if g of zi is 0, then it picks out this guy. Then zi is in this set, yeah? But this means that gamma I must be greater than equal 0, which is not possible because gamma I is less than 0. So gamma I is, or zi is not in here, and therefore g of zi so if gamma I is less than 0, then the zi is not picked out, so g of z must be must be less than. So you see, I need to do this with the case gamma I less than 0, couldn't do this with greater 0. Or otherwise I would need some here to turn some sign, but never do. But of course I could use minus g instead of d, something but. Okay, any more questions? So, we have a bound on the VC dimension, but what we actually need is not the VC dimension of A, we need a VC dimension of the set of subgraphs of G. So assume that, remark, assume that C, G, satisfies the assumption in theorem, the assumptions, theorem 3.6. Then what I'm interested in is the VC dimension of the subgraphs, the class for subgraphs of G. Any idea how I can bound this? I want to give another bound, and we can look at the subgraphs. Maybe I'll give you some hint. We see that's the point of all. Oh, I should be on this. Xt in Rd times R, where T is equal to f of x, and f is less equal than f is in G, yeah? Or maybe make it with G both times. And of course, this is not the same set as we have here, G of z greater equal to 0. Any idea what you can do?
I think you can bring it in the form of A if you subtract T.
I can bring it in the form of A is I subject B. Okay, let's try it. Xt in Rd. That's the right idea. So we make a G of x minus T greater than or equal to 0. G and G. And I want to close this bracket here. But now I need, basically here, there should be a function from a linear vector space here. Not a function from a linear vector space minus t. Any idea?
You can multiply with some coefficient to T to make it linear.
I make artificially, I make out of this one a vector, a little bit larger vector space by just, instead of writing g of x minus t, I write g of x minus alpha times t, where alpha is an arbitrary real number. Then I get a, then the whole thing is a subset of this. So we write g of x plus alpha times t, which equals 0. Here we have g and g. And now you see the set of all functions H. Consider the set of all functions. In this stage, H from D times R to R. H of xt is g of x plus alpha times c. And we have g in g, alpha in R. This one is a linear vector space of dimension r plus 1. Because you have here R basis function, and you need one additional coefficient. So you can replace this one by a linear combination of R functions, and then you have a linear combination of R plus 1 functions. Linear vector space. Dimension R. And then you see, great, we have this one is R plus 1. So it's useful, yeah? In case we have linear vector spaces, we can control the VC dimension of the set of our subspace. Or if we have finite dimensional linear vector spaces, we can control the VC dimension of the set of our subspaces, which is great. And then we can upper bound the covering number, the packing number, and also the packing covering number. Question, please?
What is R?
Assume that G satisfies the assumption in theory 3.6. That's the vector space dimension. Dimension. It's the same. Okay, great. That was not completely our chapter on 3 on generalization of neural networks. Any idea why this chapter is not complete yet? Can I apply my previous theory, or the theory which we have derived until now, to bound the generalization error of neural networks? Or that, so we have to apply to sets of deep neural networks? Where's the problem? Please.
Maybe the vector space of neural networks has too high dimension. So
Maybe the vector space of neural networks has too high dimension? No. Not true. It's not a high dimension.
Maybe we cannot use theorem 3.6.
Maybe we cannot use theorem 3.6 because
I think there's something which is not a linear vector space. Or we can use
there is something which is not a linear vector space. So the question is the vector space of neural networks a linear vector space? No, it's highly nonlinear. Yeah? No chance to apply theorem 3.6. I just have shown, well, we can apply theorem 3.6 if we just consider the whole thing as a function of the outer weights and forget about the inner weights, where we don't learn the inner weights, just choose them randomly. Then we can apply this theorem, but otherwise not. First part. And that's the reason why the next theorem I will present is the theorem of Bartlett and co-authors about the VC dimension of sets of neural network with real activation function. Another point is what you can do here. Is this surprising that you get dimension, VC dimension R? Can I bound the covering number differently? Well, if you think about a linear vector space, the linear vector space is a linear combination of basis function. And if I just make my covering such that I make a linear combination of basis function, where I allow only finitely many values for this coefficients. And now if you restrict your coefficients to the case that they are in some bounded interval, then you can put a grid on each of these intervals, yeah? And the grid size will be maybe approximate, well, say the values are between minus b and b. The grid size is something like epsilon. Then the number of discrete points you need is something like 2b divided by epsilon. And then you have r of them. So then you get a possible covering of size 2b divided by epsilon with exponent r. And if epsilon is small, and then if these functions are nicely bounded, this covering function, you will get such a bound, and it will be of the same form, yeah. Something like constant divided by epsilon with exponent vector space. But what you need in addition, you will need some bounds on the coefficients, which if I use the result which we will derive in the next lecture, or next 2 lectures, next week basically, it will be it will be a little bit more complex proof again, but nice. Which you don't need there. So you could do it, you could forget about all these different theorems, make it a little bit more different, but you need some bounds on the coefficients, which I don't want to use. Okay, any more questions? So I've printed out already what you marked for possible days of the exam, and I will make a list. I don't know, maybe for those who are here and who want to make an advanced oral exam, then maybe it makes sense if you want to mark your favorite, because it was not possible that you mark your favorite date. Maybe you just come in front before you go, if you like, and mark your favorite date, and then I will see whether you, I think I can, everyone at the moment, I can make it such that everyone gets a day where he has agreed to get which is possible for him for the exam. But maybe some of you have marked several days, and one of them I would prefer, then you can mark this day, and then I can see whether I can even reach this one. Yeah. So it's over there. You can just do it during I'm cleaning the network. Okay, see you next week. Thank you.